It's past 2. Is it okay with you, Joseph? Joseph, you can unmute yourself in the lower left-hand corner.
Okay.
Okay,
yes,
great.
so
Are you okay with it? Okay, let me, should I just start first? Okay. I would like to welcome you all to the National Engineering Month of March 2021. It has been tough here, but we are surviving. That's good, and thriving, hopefully, because of Zoom. So I would like all participants to welcome, and we have a great agenda today. Joseph is Joseph is our host. He's president of the OCI Vacuum Microengineering. I have known Joseph for quite a few years, and I know he does great job with his technology and the company that is being deployed, worldwide. So it's my pleasure to introduce to you Dr. Joseph Osiepa. Joseph, you can go ahead. Do you want to share the screen or?
Yeah, I will share the screen. And I will start my
Outline. Mm-hmm.
Presentation. Actually, I have a connection.
Your PowerPoint presentation, you can maximize the view somewhere. It's a view icon, a view icon somewhere. There it is.
Okay. Our company profile, products, and some application. In my talk, I will go through several slides showing company routes and our activities. I will touch some fundamentals for our techniques, and also I will present some product lines we currently manufacture, and then I will go to application of our products and technology, and later I will do a few comments on the global market for the new materials and related technology. In the second talk, we have a CAP student from Waterloo University, Ryan Harliński, and he will do some present application of our techniques and also actually product on some solar development. Company roots are actually back to more than 30 years ago. So my first actually experimental experience with those techniques, which is low energy electron diffraction and also electron spectroscopy, are back to my PhD work that I did in Poland. Later I did some postdoc work in Germany and in Canada at University of Western Ontario and University Guelph, and all have been related to further development of low energy electron diffraction, also spectroscopy, and different applications. So the company started in 1990 as an operation for the commercialization of those two techniques and focus on some different applications. So today, our company is one of the worldwide leader in manufacturing of low energy spectrometers, and we have a strong commitment to materials research and development. Current application of this technique, I will talk more details later, but in general, a university lab doing advanced materials research, especially focus on the two-dimensional materials, and recently energy storage materials, solar harvesting materials, and microelectronic devices. I will briefly mention about the physics of the low energy diffraction. There is a long history for this technique. Basically, this technique is based on the electron beam that it's striking the tested material surface. Some electrons are reflected back from the surface. The pattern of the reflected electrons is showing two-dimensional lattice structure of atomic arrangement. Of course, everything this happen requires special environment and condition for the electron beam, tested material, and also environment, which this technique requires ultra high vacuum environment. The key physics effect is the association of the wavelength with the moving electrons, and then this way the diffraction effect can be characterized. This is a basic picture how the basically data analysis are done and capturing. So this is the diffraction pattern with the diffraction spots, and this is the representation of the two-dimensional surface structure. And then the diffraction pattern provides a representation of this atomic structure. The question arises why this is important to know the surface structure. So the most electronic devices and sensors are built on the thin crystal substrate. So the surface is the foundation to fabricate the active layer of the device. Knowledge of the foundation structure is very important for the performance of the device. Another technique that can be actually run on the same instrument with a little bit different configuration and electronic is also electron spectroscopy. So this is another surface sensitive technique that can identify elements on the surface. It has also a long history listed over here. The fundamentals is the electron interaction between incoming electrons from the beam with the electrons which are around the atomic core shells. Results of this interaction is a three-step process and results in the emission of the electron with the energy characteristic and specific to the element. So because of that, this technique is sensitive to atomic elements and can be used as identification of the atomic elements on the surface. The penetration depth is very low, in order of nanometers. So this is the typical spectrum from the silicon carbide substrate. So this is the silicon peak, carbon peak, and this is also epitaxial film on the silicon carbide. So we measure titanium peak as well. All of the elements mostly they have different energies. So by analyzing the energy, we identify different elements. Intensity of the peak corresponds to the concentration of the element on the surface. So this is the slide with our product range we currently manufacture. So basically, this is the different sizes of the lead instrumentation. We call it classic models, from mini version that can be fit to any vacuum system, to the large analyzer that have higher angular resolution and energy resolution and a little bit higher performance. We also, through the company history, we also develop microchannel plates lead, which has higher sensitivity to the surface, and the electron beam has a very low intensity and smaller size, so that can sense structure of organic films. In-house, we're also doing electronics development. So this is our controllers that drives those systems, and so the top unit is for the lead Auger spectrometers, and the bottom unit is for the detection of the Auger electrons. We also doing in-house software development. So this is the software which actually operates with the CCD camera. So CCD camera is capturing the diffraction pattern, and for actually different structure analysis and all.
I hope we didn't, Joseph, you lost your presentation. I mean, PowerPoint.
Yeah, okay.
Could you maybe reshare again?
Yeah.
Okay, it is.
Yeah.
Okay.
Okay. I think there is some
issue, maybe internet or something.
Yeah, probably. I think I have.
We are okay now, it seems to me.
I have to share again because I think I cannot. Okay, so this is the okay, so this is the last slide. Okay, this is the Auger Spectroscopy Software, and so we do communication with the computer via USB port, and this Auger Spectroscopy software also allows for the quantitative analysis of the elements on the surface. We are also involved in more advanced development for the low energy electron diffraction. We are on this project, we are collaborating with the research organization in Tsukuba, Japan. So this is the lab with the high energy accelerator, and we built for them more advanced low energy electron diffraction that we call femto lead. The collaboration for the detector is also with the company Rentec from Germany. The capability of this analyzer for the diffraction are very high because the beam, the probing beam can have very small radius, and they can probe different scale of the materials, like insulating samples, organic films, and small domain 2D materials. This is a slide with the typical application for the silicon carbide with the epitaxial titanium film. So this is the leach pattern with a different energy. And there we observe reconstruction of the silicon carbide alloy formation on the surface. And also we can measure the purity and composition of the surface with electron spectroscopy. As I mentioned before, the other similar application will be for other semiconductor materials, superconductor oxides, and energy storage materials and energy harvesting materials. Right now I am moving to some recent application of our technique. So we find some application to lithium-ion battery anode materials. This lithium-ion battery has a getting great big large-scale production and large-scale application in the electric vehicles and the grid energy storage facilities as well. There is a need for the better performing lithium-ion batteries with the mostly higher energy density. The key problem and key properties of the lithium-ion battery are based on the lithium diffusion into anode, and then lithium bonding capacity to the anode material actually determine the energy density of the battery. We right now working on the solution to actually measure lithium diffusion characteristics on the anode material before the battery cell is actually fabricated. Right now, in order to measure lithium diffusion in the individual electrodes, they have to assemble the battery cell and use electrochemical method to measure the lithium diffusion. So lithium diffusion will affect cycling of the battery, like charging and discharging performance. So this is very important to know these parameters. The measuring lithium diffusion when the battery cell is fabricated is very complicated because all these charging and discharging properties actually involve a lot of processes that are happening in the battery, and this is very difficult to identify it as individual processes. So in our solution, we offer system like this, that this is ultra high vacuum system with the electron diffraction and also electron spectroscopy. Lithium in this method is evaporated on the anode materials, and later anode materials is transferred to spectrometer for the analysis. And this method is actually novel, and it's not used for this type of the characterization of the lithium battery anodes. To prove this concept, we characterized several basic materials that have application to lithium-ion batteries. So we characterized graphite in the form of highly oriented pyrolytic graphite, silicon and silicon carbide. Graphite, we observed that on the graphite there is strong lithium diffusion and there is no change in the surface crystalline structure. Those two patterns, leach patterns, are almost the same. So we just evaporated very small amount of lithium with the thickness 5 angstrom only. And then we don't measure any lithium peak on the surface, and only some change in the carbon peak. On the silicon, we observed that there is no lithium diffusion. We measure very large lithium peak and reduce intensity of the silicon peak. But when we do electron diffraction, we actually lost diffraction pattern. So there is a So lithium reaction with the silicon is causing formation of the amorphous or polycrystalline formation of the structure. So there is no natural diffusion. On the silicon carbide, we observe some lithium diffusion, and there is very little change in the surface crystalline structure. And then lithium diffusion peak is reduced. So this suggests that there is some lithium diffusion and intercalation process on silicon carbide. Silicon is very attractive material for the lithium-ion batteries because it has a potential, or it's already actually battery with the silicon already built, with the very high energy density, almost 5 times higher than graphite. But there is a problem that there is no natural lithium diffusion in silicon. So in order to make a good anode, there is a need for fabrication of the diffusion, special diffusion path with the nanostructure engineering process in order to provide lithium diffusion to be attached to the silicon. Silicon carbide actually is alloy, but it's 50% of silicon and 50% of carbon, and actually show very good lithium diffusion, so and no strength in the surface structure. So this is a good potential for future battery applications. So based on this measurement, we actually conclude that we can categorize those materials on 3 groups. Graphite-like materials, they have properties and no effect on structural order. In the further experiment, we actually find another materials with the similar properties, which is lithium niobate, magnesium doped. The other group is the silicon light. So there is no natural lithium diffusion, but very strong on the Hello? I think
We see you, Joseph, and hear you.
Yeah, I think I lost my.
You can unshare and share. Oh, here it is. It's coming.
Yeah. So we have another category will be silicon carbide-like materials that have a good natural lithium diffusion and low effect on structural order. So the most desired material for the high energy density should have however, strong natural lithium diffusion properties. So the lithium can be moved in and out in the battery cell, but also high bonding capacity between lithium and the anode materials, similar as silicon. So this is the slide with the system. So we have a lithium evaporation source over here. This is the lead dose spectrometer, ion pump.
Do you hear us, Joseph?
Hello?
Yes, we hear you now.
Yeah, for this technique,
We lost presentation.
Yeah, I think we are losing some internet connection.
Yeah.
So I will.
Okay, it's good now.
See if I have to. Sorry for my probably internet.
That's okay.
Connection. So this is the system we built for those measurements for lithium-ion battery materials.
So Joseph, this entire system here, arrangements you built in house?
Yes.
Yeah. Okay. Good. Okay.
Yeah. And we got last fall we got Defense Innovation Award from Tech Connect organization in US.
Okay.
So the advantages of this technology is basically that the battery anodes can be characterized up front, and this could be the selection of the anode material before the battery cell is fabricated. There is a time gap about 3 weeks between anode fabrication and the battery cell fabrication. So,
Joseph, I want to ask you a question. Do you mind if our participants ask you a question as you go along? Because it might be difficult for them to later on to remember. Is it okay with you or not?
Yeah, yes, yeah.
So anybody, if you are interested in a certain area, feel free to ask a question, Dr. Joseph Osiepa. Okay, thank you. You can carry on.
So basically, we are right now in the process of finding new application in the battery market for this system, and doing the in advance battery anode characterization and saving on the elimination of the battery fabrication process from the bed batch of the anode materials. So this is actually my last slide that I want to touch some general comments on the global market and future to this type of the technique and characterization. So everybody knows that silicon-based devices revolutionize global market for microelectronic devices, sensors and communication devices for last few decades. However, silicon have a limited power efficiency, high losses, and poor tolerance to temperature. So there is a need for the new materials that will overcome those limitations. And thin crystal oxides substrate recently emerged as an important class of multifunctional materials with a rich collection of properties to be explored. The new application for the thin crystal oxides are high mobility transistor, gas sensor, actuators, acoustic transducers, photovoltaics, energy harvesting, energy storage devices. One of the examples is gallium oxide material. We've been also involved in basic characterization of this material. The gallium oxide has high temperature tolerance and high chemical stability. And this is the wideband semiconductor with a high potential for the high voltage, high current application as a transistor diodes and also as a solar blind UV detector. The gallium oxide can be economically fabricated and has excellent chemical and thermal stability. So right now, gallium oxide is considered as an important component for the third generation of the semiconductors. So working with this material, we are showing capability of our technique and trying to enter this also semiconductor market with our techniques and products. So that's conclude my presentation. So you can also maybe, I don't know, ask me the question right now, and later on we can move to presentation from Ryan.
And anybody has a question, feel free to ask Joseph. And you can unmute yourself. Unfortunately, I don't see everybody here. So I think that you have an icon down there, unmute. If you have a question, feel free to do so. Are you, Joseph, going to talk about global markets, or you will talk about that later?
I already touched this. Yeah.
Okay, good. Okay. If not, then maybe perhaps I don't see anybody. Oh, there is a question here online. What applications, came from Brendan Campbell. What applications does this research have beyond batteries?
This can be applied also to any thin films coating and new generation of semiconductor materials.
Okay.
So on the previous slides, I mentioned about the gallium oxide materials, and that is under development right now. So the surface characterization and diffusion processes and defect characterization are very critical for the total performance of this type of the devices.
So if anybody wants, there is a chat room down icon. You can put your questions down there, or you can unmute yourself and ask. Okay, maybe we should move with the next presentation, or whatever you feel, Joseph, is appropriate.
Yeah. Ryan, could you?
Joseph, you have to get out to unshare your document so that Ryan can
okay,
do that.
I think I got it. You can see my screen, right?
Yes.
Hello? You can hear me as well?
Yes.
Okay, sounds good. All right. So, hello, everyone. My name is Ryan Cherlinsky, and I'm a second-year chemical engineering student at the
We have some problem, Ryan. We have some problem with audio.
Is that better?
I don't know. Go ahead. Let's see.
Could you hear me now?
Yes.
Okay, so here's a brief outline of my presentation. I'll be covering the science, engineering, eco methodology, and testing and analysis conducted so far. So OCI is currently in the phase 1 development of our solar shutter project. Over the past 2 to 3 months, we have been designing and modeling the shutter concept, fabricating and testing initial prototypes, researching optimal applications, and have begun to research and develop a new high efficiency photovoltaic cell. Here we can see some of the renderings on various shutter designs we have done. The main premise of our solar shutters is that they function as typical window shutters with PV cells between a frame and bracket. The goal is to provide the shading comfort of regular shutters while simultaneously taking advantage of incoming sunlight. So at OCI, we have conducted initial research and development on a stacked junction silicon germanium cell with a theoretical efficiency of 34%. This compares to the average 22% current silicon cells on the market, and 54% of sunlight respectively, seen in the pie chart.
Ryan, could you for some reason we don't hear you well. We don't hear you. Ryan, we don't hear you.
Yes,
don't know.
can you hear me? Can you hear me now?
Yeah, we do now.
Okay, I'll just have to talk louder.
Repeat that, yeah.
Okay, so the conventional multi-junction scheme seen in part A in the top right figure places these cells in series. This requires current matching because germanium generates much less current than silicon. Could you hear me or not? Okay.
Yeah, we heard you now.
Okay, so while in series, the efficiency is limited to the germanium's performance, which is only around 5% efficiency. In the stack configuration seen in part B, the cells are isolated, so current matching is not required, and the efficiency is simply the sum of the two cells. The buffer layer that isolates the silicon and germanium must be able to transmit infrared photons and have good passivation properties. Samsung was able to develop a buffer layer. However, it absorbed too much infrared, reducing the performance of the germanium cell. At OCI, our ultra-high vacuum systems have capabilities to grow and test buffer layers in efforts of achieving this 34% efficiency stack junction cell. We have indication of promising buffer layer materials that will be further tested in the near future. Achieving this buffer layer will be a groundbreaking moment in photovoltaic stacked junction cells, which can be applied to increase the efficiency of typical large-scale solar panel systems in addition to our solar shutters. So engineering. The basis of our mechanical motion consists of a rack and pinion system, which will open and close the shutters as seen in the animation. There will be an additional pinion at the end of the rack that is turned by a motor. The wooden dowel frames contain slots to fit the PV cells and have a counter bore feature, which allows the shaft to remain hidden and not take up any PV cell space. Hopefully you can see my video. Here I have a sample bracket. So we just drilled directly the dowels in. The wiring can fit through this slot here and up the shaft, so it doesn't interfere with the shutters. Yeah, so the electrical connections extend out the back of the PV cell and run through the shafts on both ends into the main frame. Our current prototype will be around 110 watts for this window, which is approximately 2 by 6.5 feet. Looking forward, solar tracking technology will be explored so that shutters could automatically rotate to face the sun and provide shading. The shutters in this video on the right are currently controlled via remote. The location of the shutters, interior or exterior of the windows, will depend on the ability of the window to transmit visible and infrared light. Typical transmissions are currently being tested and analyzed. So we have conducted various lab and field tests and analysis to guide our design decisions. First, we conducted a mechanical strength testing of the frame materials. The purpose of this experiment was to compare the relative strengths of materials such as wood, aluminum, and bamboo. This was a very simple experiment consisting of applying a weight on the material and measuring the displacement. We found that generally wood was more sturdy than aluminum and bamboo, so we decided to continue with wood for our initial prototypes. We also conducted an analysis of potential energy generation solar panels on building facades. These simple calculation capacity could 961 kilowatts of power on the south facade of the One London Place, which is the tallest building in London, and 100 kilowatts of power on Robarts Research Institute at Western University. Most recently, we explored window coating effects on interior solar panel output. These focused on low E coatings, which transmit visible light but blocks infrared. Field tests have been conducted at the Amit Chakma Engineering Building with their state-of-the-art windows, and lab testing has been conducted at OCI recently. Due to low E window coatings absorbing and reflecting sunlight, solutions include exterior window shutters or interior shutters in between clear glass and a low E coating. These solutions will be explored in the coming months. Eco methodology. Throughout the design and development of our solar shutters, we were considering the environmental impact via life cycle assessment performance. This includes expenditures such as energy consumption and greenhouse gas emissions at every stage of life, from extraction of raw materials to end of product usage. We believe in investing in clean and efficient energy sources as per the 2050 global net zero emissions goal. Solar energy is a very promising area of development, as seen in recent increases in capacity and generation. So, while we are currently fabricating and testing horizontal-oriented prototypes for smaller windows, as seen in my previous slide, our future goals and ideal applications will be to scale upwards to vertical shutters on large windows in high-rise buildings. These buildings are ideal for solar shutters, as the facades are typically all glass, and there will usually be very little rooftop space for typical solar panel systems. We believe that this would be an exciting step towards achieving net zero energy and emissions if successful. So, yeah, that is all for my presentation. Thank you for listening. And I guess the floor is now open for any questions. Thank you.
Oh, thank you very much, Ryan. Really appreciate it. Those are good slides that you presented. They give a visual representation of your project that you are, so you are collaborating, Joseph, with the University of Western Robarts Research and Faculty of Engineering?
Yeah, so those are more just taken from, we just took images from Google and Google Maps and sort of did our own calculations.
I see.
But we did get permission from the Dean of Engineering to examine the windows at the Amit Chakma Engineering Building to see how their windows affect the interior solar panel output.
Mm-hmm. Tell me, that building, Chakma Engineering Building, isn't it already eco sort of a kind of a building that they built into their, just glass windows, or not yet? Would you know?
Sorry, I missed that.
That Chakma engineering building at UWO, University of Western Ontario, is already so-called eco building.
Yes, so that building is the first LEED certified building on campus.
Yes.
So it provided a good opportunity to test interior solar panels to see how the window coatings, so their windows are very high performance in terms of not allowing heat inside the building or allowing heat to escape, essentially providing the same efficiency as a wall. And so we just wanted to see if there was enough light passing through the windows for interior solar panels to still generate electricity.
Okay, thank you.
But yes, the building is very energy efficient.
Okay, okay, good.
Yeah. And to answer Abdu's question for how the system is sensitive, for how the 34% efficiency is sensitive to temperature. So we haven't done any testing regarding that, but I would expect for the sensitivity to not really change. For example, current solar panels with silicon cells, they're able to withstand temperatures up to 100 degrees, I believe. And we expect that with the addition of the germanium coating, the temperature shouldn't, the sensitivity to temperature shouldn't change too much. If it does, we would have to include a layer of coating or something to block the heat. But yes, we will explore that in the future. That's a great question. Thank you.
Okay, good. Okay. Somebody, yeah. The other has a question, feel free to ask either Ryan or Joseph. Okay, there is another question by Lori. Okay.
Hello, I don't have a question. I just wanted to say thank you for the presentation, and I can picture the building since I work there.
Good. So
Thank you, Ryan.
how do you feel working in that building?
The temperature is very well regulated. Yes,
Okay.
and the windows are beautiful.
Okay, thank you. Okay. Anybody else? Feel free to ask the question.
Yes, Ryan, this is Brian here. Would an eventual goal of the solar panels, I know some houses have solar panels on their roof to generate electricity for the grid. Do you envision the louvres inside the windows to compete with that degree of energy production?
Yes, great question. Thank you. So I believe there is a certain threshold you would need to meet to be able to contribute to the grid. And depending on the sizes of the buildings, of course, in typical houses, the windows are not big enough to, or probably will not be big enough to achieve this threshold. So we would just be expecting the solar panels to be hooked up to a battery, and then the battery can then be used to power appliances throughout the house, such as toasters and such, or just lighting. But yeah, directly contributing to the grid, that would require a much larger system.
Okay, thank you.
There is another question from Rob Dijon. Could you read it on your chat?
Yeah, okay. So Rob, yes, has OCI had any discussions with Ontario manufacturers that buildings. So to answer that, no, currently we're just contracted with innovative solutions Canada for this
Ryan,
phase one project.
we
And
have
then
a
we will
problem. We have a
continue.
problem. We have a problem hearing. you.
Yeah,
Could you repeat that again, please?
I think I'm good now.
It seems to me.
Darn it.
Go ahead. No.
Sorry, I think my connection is shaky, but
You're
I'm
okay now,
good
it
now.
seems to me. Go ahead.
yeah, so I'll continue. So currently we're just in phase one with Innovative Solutions Canada. And if we are successful and they like our product, we could move on further. So right now we are not in any discussions with them because we are still very early steps of the project. But in the future, we will definitely try to extend our outreach into contacting these larger manufacturers and partnering with them.
There is another question by James Singro. How fast imaging system works using long sputtering gun? That's maybe for Joseph.
Okay, yeah. Are you hearing me well?
Yeah.
Yeah, so our imaging system with the CCD camera is designed to the low light intensity because diffraction images doesn't have a very high intensity. So basically we are integrating images on the CCD camera for about 500 milliseconds or so. So basically, this is not very fast measurement, but because of the low intensity of the images. So we with this diffraction system, we are not doing very fast measurement.
Hi, so I just want to ask, what is the surface we can cover with the imaging? Like, I'm just looking at the specification. The beam size is about 1 millimeter to 250 micrometer. So is that the within 500 millisecond? Are we talking about just taking picture of that 1 millimeter square surface?
Yes, yeah.
So let's say if we have a bigger surface, 10 millimeter by 10 millimeter, then we have to keep capturing by moving the gun, sputtering gun, or how does it really work if you have like bigger surface?
So you can with this experiment, in order to have a symmetry on the diffraction pattern, there is no deflection plates on the electron beam. So if you want to scan a larger area of the wafer, you basically have to motorize the sample holder and slowly rotate and move the sample in front of the lead detector. This way you can scan whole sample.
You have the technique that you developed in house, Joseph, or?
No, we moving the sample. We are building not very often, but we can offer such a solution. to this configuration. So right now, we've actually with collaboration with another company, VacGen in UK, we are providing 5-axis manipulator. It's a little bit for the different experiment, and then all the manipulation is done not on the electron beam, but all the manipulation like rastering in front of the detector or rotation and other angles are done by manipulation the sample. So we can provide such a solution. Yeah.
So that was the next question. How do you focus on the surface? So do you have to like manually rotate so you kind of get the better picture, or how exactly works? I mean, taking the picture from the after you use this the gun.
So usually the best would be to make all the detection in one plane, so then you don't have to change the focus. But the one focus voltage we are doing manually. Also, we can control via the computer. And then this can be adjusted if the sample is moving not in one plane, but it like in three-dimensional plane.
Yes, thank you. That's so the complexity is based on the application of the user, as I understand. So we can customize it, right? So you guys only provide the solution for like sputtering gun, and then it's based on the customer how they're gonna use it. So as I understand, is that how it works?
Yes, that's the most cases situation that that we are right now providing. But we also, because the sample manipulation is a part of the large ultra high vacuum system. So if somebody or someone is interested in the complete solution, like complete ultra high vacuum system, we can include the advanced manipulator with up to 5 axes of movement.
Yes, thank you. Thanks for answering the question.
Okay, there was a question. How our technique is different from the reflectance spectroscopy. Yeah, so reflectance spectroscopy is based on using, I think, I'm not that expert on this, but it's based on laser light. We are and then probing the surface with the laser. So it's a different technique and different kind of results. With laser, with light, you cannot get atomic structure. You might have some kind of topography and defects, and it's very powerful technique with detecting microscopic defects, but you can't get diffraction pattern with light from the surface.
Okay, Joseph, we can move to the other part of presentation.
Hello?
Yeah, we hear you. We are waiting for your. Are you going to move to the other part of presentation about markets and those things? So, or this is it?
Oh, this is it. Yeah.
Okay. Okay. Good. Anybody else has a question? I know this is highly technical area, but feel free to ask either Ryan or Joseph. So, Joseph, if I may ask a question. So this window shutters, I mean the solar, so this project has been partially funded by Innovation Canada, am I correct?
Yes. Yeah.
And when does this project supposed to be done and finished?
So this is the phase 1 of the project. So it will be finished in July this year.
July this year, okay.
So this is the phase 1 is like a proof of concept and visibility for this type of the technology and potential application, or the area for the buildings which has more benefits will gain more benefits from this type of the shutters, solar shutters. So there is the glass window, the large glass walls are very popular in the high-rise building. And so I think there is a potential in the high-rise building in the downtown special area, and if any solar energy can be retrieved in downtown area, and the only solution will be the walls, because the roof area is very small and all the utilities are on the roof. And then there is no any other area to be, to be exposed to sun. So on some building there is also, you have the windows, but also you have walls and some cladding. There is a possibility for some solar cladding on the regular high-rise building wall as well, but we are not exploring this technology at the moment.
Mm-hmm. There is another question from James Sangro. How long does it take to manufacture the device? I don't know, James, which device did you refer to?
No, I
So-
will.
Yeah, there's like very complex device. I'm just looking at one of them. Like let's say IMBE 300 model number. So it looks fairly complex system. And there's another one, IMBE 300B, basic configuration. So like, to make that, how long would it take? Let's say customer wants to order one of them.
For this complete system, we need from 6 to 9 months time slot from the order to delivering the system and installation and training. Yeah.
But you have in-house, what I've seen in inventory, some components that are pre-machined. Am I correct?
Yes. Yeah.
So that speeds up a little bit, the delivery.
Yeah. So the components, our components, we are building quite fast. So right now, in the present, situation, we need like 4 weeks from order to shipment, but we can do even faster. But this is our standard product. The MBE system usually requires special configuration for other components or different sources for evaporation of different technique, or combination of the different technique for the deposition. And then we have to collaborate with our vendors, and then even design process takes a little bit time. But usually there is nothing like standard system for this molecular beam epitaxy system. Every system is actually different.
Joseph, if I may ask you a question, let's say in general, because your company is vertically integrated, that means that you manufacture from design to manufacturing most of the components in-house. How many components do you need from the vendors? Like percentage-wise, let's say for a system, is it 10%, 20, 30%, and the rest of it is in the house? Roughly.
Yeah, so because we have what developed machine shop, like we have five CNC machines right now and some manual machines. We are making actually 90% of the components to our leaders analyzers and ion sources or electron sources. So we supply ourselves a lot of parts. For the complete system, we have to collaborate with vendors, and then our contribution, our components to MBE system are estimated to be in 55 to 60%.
Thank you. Thank you. So where in majority, what is the best market for you, for your systems that you manufacture? Is it Asia, or is it Europe, or is it North America, or?
No, but actually everywhere. So we don't have it's a little bit changing, but right now it's very very uniform. So Europe is very good market. Then we have a market in China. We have also good market in Japan, and pretty good market in United States as well. Not that much market actually in Canada. So 95% of our sales are export. So that's the situation.
What I understand, you are a rather unique company. You are the only manufacturer of this type of equipment in Canada. And how many are there in the world, including you? About five companies, am I correct?
Yeah, 5 companies, yeah.
Okay. So 2 of them are in USA, 2 in Germany, or where? In Europe.
Yeah, so yeah, 2 in USA and 2 in Germany.
I see. It's a highly specialized
Yeah.
company. Okay.
So actually in Germany is right now only 1 company. So actually altogether there are only 4 manufacturers worldwide.
I see.
There is no manufacturers in Japan and no in Asia.
In China, no?
No, in China.
So you have in China, you have a market, Japan, Australia. Do you have any product in New Zealand? No.
Maybe 1 system, yeah, I think so. We have 1 in New Zealand.
Europe, yeah.
Yeah, a lot of in Europe. A lot of in Europe.
Okay.
And most of our products actually we have our users in Japan.
In Japan. So they are heavily involved in research and development, like universities or big corporations?
In Japan, we have universities, then we have a government lab. There is a quite large number of the different government lab besides universities.
Okay.
And we have also customers, big corporation laboratories for big corporation like we have in Toyota, we have Hitachi, Sanyo, all these big electronics manufacturers.
How about Korea and any of those? Or?
Yeah, in Korea, mostly universities. We have also very good market in Korea, very good market in Taiwan, but we have also customers in Singapore, but mostly universities.
Okay.
We have quite a few installations also in South America, Brazil, and some in Argentina.
Okay, good. So hopefully this solar application, I mean, window shutters and batteries for you, that would be sort of diversification of your business. Am I correct? So into different areas a little bit. Or do you work with your potential end users of batteries to improve their performance? And the shutter, you are going to provide them with a service, or do you want to diversify in some of the components?
So for the solar project, we have 2 components. So one is the engineering component, and then there is this, science component. So the engineering component is about mechanical movement and the proper design and to get most of lights basically into the solar cells, and then but we are also doing scientific concept that we want to increase energy efficiency by capturing the infrared part of the solar spectrum, but working on the kind of a backside of the silicon wafer. So with this engineering background, we are gaining some knowledge and also some experience with the solar panels. But if the scientific or if the science project is successful or leads to be very successful, we just trying to focus more on the development of the solar with the higher efficiency at the just solar cells level.
Oh, this is the question from James. I hope that has been answered already. Do you have to manufacture in a vacuum or a clean room?
No, we don't use vacuum for the manufacturing, but we use a clean room for the final assembly. So all the spectrometers has to be assembled in the clean room environment, and we are using some technology for the clean room over here in a modular kind of as a clean room benches solution. But all the testing of the components has to be done in ultra high vacuum.
Okay, thank you.
So, yeah, I was just curious, like if you use clean room, must be the maintenance of the clean room usually very expensive as well, right? You have to use a lot of energy. But you said you use a smaller clean room, like a box clean room. You said, or is it? Do you have a big clean room?
No,
facility?
we have a we have a we have a kind of a separated small room as a clean room, and then in this clean room we have another bench type of the clean room. So actually we have in this clean room we have 3 benches that actually provide even a cleaner air, and in this clean benches we are able to maintain higher purity of the air, because the purified air is coming from the top, and then in this environment the final assembly is performed.
So this manufacturing, like the clean room, how they control the quality? Is there any standard required by the customers as well, or do you guys have your own quality control, like a standards, some sort of?
So we are using, we have a different particles meter. So we test. We have I think right now, because we use some of them for purification for COVID applications. So we've been testing also like HEPA purifier for COVID, but on the clean benches we test basically with this laser particle counters, what level of filtration we have, and then actually our spectrometer is sensitive to dust. So basically when we're doing testing in ultra high vacuum and we have some dust deposit on the energy analyzer, which is a part of this imaging, detector, we see what's going on. So because the dust is, so if we're using very low energy electron, the dust particle is actually charged by the electrons and then show as a dark spots on our luminescent screen. So we measure this situation, at the quality control testing as well.
Good.
So basically, we have using this, we kind of develop our own standards for the ultra high vacuum testing for the dust particle on the analyzer component. But for the HEPA filters, we are using this laser particles counter, and they have a sensitivity 0.3. They have like the maximum sensitivity for the small particles. They have 0.3 micron. So basically, if we are making sure that this reading, the reading is in the 1 liter of the volume of the air we are testing, this has to be 0. So if we see all 0 on this particle counter meters, we are okay, and we are doing assembly. But sometimes during transferring the analyzer, or sometimes there is some particle escape. Just one particle can make some kind of effect on our analyzer, and then we have to disassemble, clean, and assemble again, and test again.
Thanks. Anybody else? Just I have a question for you, James. I think at Quantum 5X, you have no need for clean room, do you? Or
No, we don't usually use clean room, but sometimes we have a problem of keeping the dust away, because we have LCD screen, and sometimes the dust goes onto the a plastic cover, so we have to get rid of that. And usually, I think, in general, when you're assembling a sensitive device, you need a cleaner environment, even the electronics, because of the dust can create some spark, and it can even create a fire, right? So I was just curious. Yeah, no, we don't usually use like a clean room, but it's a nice thing to have if you can create that clean room. For our product, not really. We don't usually assemble it in clean room.
Thank you very much, James. I think we are coming to the end. Joseph, would like to say anything else, or Ryan, at this stage?
No, I would like to thank you to everyone for this meeting and very interesting conversation. And basically that's all. So if someone has any further question or some comments, please email me, and we can discuss some topic later on.
Okay, we have a survey here that has been put together. We want to know what you think, please. Okay, so we have okay, so that's 100%. Okay, good. Share. So how do I do that? Okay. Sarah?
Hi, George.
How do you fill this in? Just
Just the co-host can't, it's just the participants that answer, so don't worry. I can see that 3 people
oh,
have
that's for
voted.
participant. Okay, good,
Yep,
good.
yep.
Okay, okay. Not for me. Okay, that's
Yeah,
okay.
no,
I'm
you just
glad.
need to launch it.
I'm glad.
Yep, it's all good.
Okay. Okay.
Yeah, we can just give them a couple more seconds. Almost everyone's voted and we're all good.
Sure. Okay, well, they are doing that on behalf of National Engineering Month, Professional Engineers Ontario, Society of Professional Engineers, and London chapter. I really appreciate your participation and would like to thank to Joseph and his team at OCI. And I would like to also thank to Ryan for his excellent presentation. It was very well done. And I wish you good luck with your further research and study. So you'll be staying in touch. If you have any question, Joseph, feel free to get in touch with us. And wish you good success with your projects. Thank you all. And in particular, I would like to thank to Sarah. She's been great facilitator.